Okay, so now let's do one example to show you how we can use those tables to look for internal energy, lowercase u, and enthalpy, lowercase h. So here we have one example. The substance we have here is refrigerant 22, and we know the temperature is at 12 Celsius. We also tell you the specific internal energy, lowercase u, of refrigerant 22 at this temperature is 144.58 kilojoule per kilogram. And we're looking for X, which is quality, and the lowercase h, which is specific enthalpy. Okay, so before we look for quality and specific enthalpy, the first thing we have to do is to find out what is actually the phase of refrigerant 22 at 12 Celsius right now. And then, based on what the phase is, we can make a plan on how to look for enthalpy H. Okay, all right, so let me quickly show you how we can do that. First of all, we're gonna have to go to a table to look for refrigerant 22. And which table is for refrigerant 22? Let's go to the thermodynamics tables. And here you can see I have table A7, table A7, and table A7 is for refrigerant 22. So make sure you use the correct table based on what kind of substance you have. Okay, and then after you locate the table, what can we do next? We also know the temperature is at 12 Celsius. So we go to the table and we look for the first column. First column is temperature and the unit is Celsius. The temperature we have is at 12 Celsius. So 12 is here. 12 is here. So now you can find all the properties in this row corresponding to temperature of 12 Celsius. All right, as highlighted in this row. Okay, so now for example, we know how to look for nu f and nu g. They are in column number 3 and column number 4. We've been practicing that. And then now if you move to the right, continue from nu, what do you see? In this column, you can see you can find nu f, specific internal energy of saturated liquid. And then next to uf is Ug, that's specific internal energy of saturated vapor. Okay, and then if we continue to the right, you can find HF. And what is HF? Specific enthalpy of saturated liquid. And then if you continue to the right, here Hg. Hg is specific enthalpy of the saturated vapor. And be very careful. What's between HF and Hg is called HFG. And what does HFG mean? HFG is equal to Hg minus HF. It's the difference between HF and Hg. Make sure you look for the one you want. So for example, if you're looking for Hg, make sure you go to the correct column because sometimes when students look for Hg, they go to column HFG and then they find the wrong solution. Okay, so make sure you look for your number in the correct column. All right, so now what we can do is we can write down all those properties. That's what I usually do. Okay, so now, for example, what can we write down? For this example, it seems like we're not dealing with nu. So what we probably need is UF, which is 58.77. We can also write down UG, 230.38. And then at the same time, we can also write down HF, 59.35. We can also write down HG, 253.99. Okay, so that's what I'm gonna do. I will go back to the notes and then I'll write down the properties. We went to table A7. We started from temperature equal to 12 Celsius. And from the table, we found those following properties. First one we found was UF, lowercase uf, 58.77. Don't forget the unit. If you don't remember the unit, you can just go to the top of the table and you can find out the unit. We also found lowercase ug, which is 230.38 kilojoule per kilogram. And in addition, we also found lowercase haf, lowercase hg, specific enthalpy for saturated liquid and saturated vapor. The first one is 59.35, and do not forget to write the unit. And Hg has a value of 253.99 kilojoule per kilogram. So now we can continue. Okay, so the first thing we said we need to do is to decide what is actually the phase of the refrigerant 22 for our example. There's one way to decide by comparing the internal energy. Okay, so I hope you've noticed. We told you for this example, our internal energy, our specific internal energy is 144.58 kilojoule per kilogram. And then we also found UF and UG. Is it possible for us to find out what the phase is based on those three numbers? Yes, it is. So for example, what is UF? UF is how much energy you have when it's at saturated liquid. And UG is how much internal energy you have at saturated vapor. Okay, so for example, our actual U is 144.58, which is between UF and UG. What does that mean? That means our substance must be between point F and point G. If our substance is between point F and point G, then it must be a mixture of point F and point G. What if our actual U is lower than UF? Then the substance will be at subcooled. What if the actual U is even higher than UG, which means it has more energy than saturated vapor? That means the substance must be superheated. So by comparing those three numbers, we can find out what the phase the substance is at. Okay, so we can write down because our U because our U 144.58 is between UF and UG. Then we can say the conclusion is it must be a mixture. It must be a mixture. Okay, so now since it is a mixture, quality X must be between 0 and 1, not including 0 or 1. So the first one is to look for X, quality. How do we look for quality? Which equation do we have that has quality inside? Let's go back. Do you remember we have those three equations, nu, u, and h, when you have a mixture. And in those three equations, we have x showing up. So probably we'll use one of the three. And which one do we use? We have u, we have uf, we have ug. So obviously we're going to choose the second one. So we start from the second equation. U is equal to 1 minus x times uf plus x times ug. Okay, let's take a look. What do we know and what do we not know in this equation? We do have u, we do have uf, we also have ug, and the only thing I don't have is quality x. One equation with only one unknown. This is perfect. We can easily look for x. Okay, so then what you do is to perform algebra. Move x to the left-hand side and then everything else to the other side. Okay, so the solution is u minus uf divided by ug minus uf. Okay, It will help you a lot if you can memorize this format. The format of this algebra is actual, which is u minus point f, and then divided by g point minus f point. Okay? Alright, so now we can plug in the three numbers. U is equal to 144.58 minus UF, which is 58.77, divided by 230.38 minus 58.77. They have the same unit, which is kilojoule per kilogram, and it's okay even though kilojoule is not SI because they will all cancel because this is a division, so the units will cancel. The solution is zero point 0.5 and our solution doesn't have a unit because all the units have cancelled. Okay, so that means 50% of our mixture is actually saturated vapor, and then the other 50 is saturated liquid. So this is how you look for quality X. And now, next question is to look for specific enthalpy, lowercase h, of this mixture. How do we look for h when we have a mixture? And again, we go back to those three equations, and this time, since we're looking for h, we're going to use the third one. Okay, so the third one is h is equal to 1 minus x times hf plus x times hg. And we have everything in the right-hand side, so we just plug in all the numbers. 1 minus x, which is 0.5, times hf. We found hf and hg already earlier from the table. So we plug in hf. hf is 59.35. And then plus quality 0.5 multiplied by hg. And hg is 253.99. Okay, so the solution for h is 156.67. And what is the unit to the solution? First of all, quality doesn't have unit. And what is the unit we used for HF and Hg? We used kilojoule per kilogram. So our solution must also have kilojoule per kilogram.